Next chapter, X-rays. Now, we have seen how cathode rays are produced, and we know that these rays are no more than just a stream of electrons produced at the cathode through thermionic emission and then accelerated through a vacuum tube towards an anode target. This is the sort of thing that fascinated the scientists of the day, and as they continued to experiment further, this led to the discovery of not just the electron, but also the discovery of X-rays. X-rays were discovered by Wilhelm Conrad Röntgen in 1895. He had photographic plates which were kept in a dark container so that light could not get to these plates. These were then kept in a drawer. For some reason, Röntgen decided to develop the plates after having played with his cathode ray tubes. Now, remembering that light from the tubes had no way of getting to the plates, yet when he developed the plates, they were exposed. There were markings that should not have been there. And this meant that some invisible radiations had penetrated the container and reached the plates. And because he did not know what these radiations were, he called them X-rays for unknown rays. Today, we know that X-rays are produced when fast-moving electrons are suddenly stopped when they hit a metal target. In 1913, Dr. William Coolidge designed an X-ray tube for the production of X-rays. This tube is also called the Coolidge tube. It consists of a highly evacuated glass bulb containing a cathode, which is a tungsten filament, and a target, which is an anode made of a metal of high atomic weight. When the cathode is heated by passing a current through it, it emits electrons by thermionic emission. The tungsten is surrounded by a molybdenum cylinder, which is kept at a negative potential so as to repel the electrons produced by the filament. These electrons are then attracted by and accelerated towards the anode, that is the target. The target is made of a copper block in which a piece of tungsten or molybdenum is fixed. A lot of heat is produced when the electrons hit the target, and copper, being a good thermal conductor, carries the heat away to the cooling system. The target is also tilted at an angle of 45 degrees, causing the electrons to hit at an angle. A very high potential difference in the order of 100 kilovolts is applied between the source and the target. Due to this high potential difference, the electrons are accelerated from the cathode to the anode, and when they hit the target, a part of their kinetic energy is converted into X-rays. The intensity of the X-rays depends on the number of electrons hitting the target. Now, let's look at a simplified model of the X-ray tube. We have the evacuated glass tube. In the one end, we have the thermionic cathode made of a tungsten filament. The anode is located at the other end. From a high voltage source, the positive terminal is connected to the anode and the negative terminal to the cathode. The cathode is heated by an electric current, causing thermionic emission of electrons from the tungsten surface. When the high voltage is switched on, the electrons are accelerated towards the anode target. When they hit the target, some of their kinetic energy is converted to X-rays, but much of it is converted to heat, which has to be dissipated by cooling. Because the target is inclined at an angle of 45 degrees, the emission of X-rays is more to the right, but a small portion radiates in other directions. A protective housing shields the X-rays from going in unwanted directions. The desired X-rays can only reach the outside through a small transparent window. With this setup, A high resolution is not yet possible because of the large area on the anode where X-rays are generated. This produces diffused X-rays. To solve the problem, an electromagnetic lens is used to focus the electron beam at a small spot on the anode surface. The smaller the focus spot, the sharper the X-ray image will be. It is important to note that when the accelerating electrons hit the target, 99.5% of their kinetic energy is converted to heat. And that means only 0.5% is converted to X-rays. Heat dissipation is the greatest challenge in the design of an X-ray tube. As electrons come over from the cathode, they strike the anode, producing a lot of heat. To spread that heat over, modern X-ray tubes have rotating anodes. This prevents the heat from being confined at one point. Dental X-ray machines use stationary anodes, while general-purpose radiography machines use a rotating anode. Next, properties of X-rays. X-rays are electromagnetic radiations of shorter wavelength than visible light. This means they can be polarized and diffracted because they are waves in nature. They travel in straight lines at the speed of light, that is 3.0 times 10 to the power 8 meters per second. They are not charged, so they cannot be deflected by electric or magnetic fields. They penetrate matter with the least penetration occurring in high-density materials like lead. They affect photographic emulsions and are therefore used in X-ray photography. They cause photoelectric emission. They also cause fluorescence in certain substances like zinc sulfide. In moving through air, they can knock out electrons from gas molecules in their path, causing ionization of the molecules and thus increase electrical conductivity of gases. Polarization and diffraction experiments on X-rays by crystals have confirmed the wave nature of the X-rays. X-rays are electromagnetic waves of very short wavelength of the order 10 to power -11 meters. In fact, electromagnetic waves in the range of 10 raised to power -11 to 10 raised to power -14 meters are considered as X-rays. This range overlaps with the UV at the upper end and the gamma rays at the lower end. Next, let's talk about the energy of X-rays. Now, the energy of any electromagnetic wave is controlled by the wavelength and the frequency. We know the wavelength is the distance between two peaks or troughs. When the peaks are closer together, the wavelength decreases. But when the wavelength decreases, the frequency increases, which is the number of wave cycles per second measured in hertz. In this case, the frequency is about 2.5 cycles per second. Both the wavelength and frequency affect the energy of a wave. For example, both of these photons are traveling at the same speed, which is the speed of light. The only difference is the wavelength and the frequency. The upper one has a long wavelength and therefore it has a low frequency and a very low energy. The lower one has a very short wavelength, resulting in a higher frequency and therefore higher energy. Remember that when an electron is suddenly stopped at the target, much of its kinetic energy is converted to heat and a very small amount is converted to X-rays. For a given accelerating potential difference, the X-rays produced have varying wavelengths. The shortest wavelength, lambda minimum, corresponds to a collision in which all the kinetic energy of the electron is assumed to have been converted to X-rays. The kinetic energy of the bombarding electron is equal to EV, where E is the electron charge and V the accelerating potential difference. If all this energy of the electron is used to produce the X-rays, then the frequency of the X-ray radiation will be maximum, that is F maximum. Recall from the previous chapter that the energy E of a radiation or a photon is given by E is equal to HF, where H is the Planck's constant. So in this case, kinetic energy of the electron will be equal to the energy of the X-ray produced. That is, kinetic energy is equal to E, meaning that EV is equal to HF maximum. And that is because when lambda is minimum, frequency is maximum. We call that equation 1. Recall also that C is equal to F lambda, where C is the speed of light. This means that F maximum is equal to C over lambda minimum. Substituting in equation 1, AV is equal to HC over lambda minimum. So the X-ray beam is what we call polyenergetic. And that means there's lots of energies corresponding to the different photons with different wavelengths. The most energetic X-rays have the shortest wavelength, given as EV equal to HC over lambda minimum. Let's take an example. An X-ray tube has an accelerating potential difference of 100 kilovolts. Calculate A, the kinetic energy of the electrons, B, the highest frequency in its X-ray beam, and C, the shortest wavelength in its X-ray beam. We start with A, the kinetic energy. Kinetic energy is equal to EV, 1.6 times 10 to power negative 19 coulombs times 100,000 volts, that is 100 kilovolts. That gives us 1.6 times 10 to power negative 14 joules. B, maximum frequency. This will be achieved when all the kinetic energy is used to produce X-rays. In this case, kinetic energy will be equal to EV, which is equal to HF maximum. And that means F maximum is equal to EV over H. We already have EV, so F maximum is equal to 1.6 times 10 to power negative 14 joules over 6.63 times 10 to power negative 34 joules second. And that gives us 2.4 times 10 to power 19 hertz. And finally C, the shortest wavelength, lambda minimum. This occurs at F maximum. We know that C is equal to F lambda, and so in this case, C will be equal to F maximum times lambda minimum, meaning that lambda minimum is equal to C over F maximum. That is 3 times 10 to power 8 meters per second divided by 2.4 times 10 to power 19 hertz, and that gives us 1.25 times 10 to power negative 11 meters. Next, we talk about hard and soft X-rays. Now there are two types of X-rays, namely hard and soft. Hard X-rays are produced by fast-moving electrons as a result of high accelerating potential difference. They have very short wavelength and thus high penetration power. They can penetrate flesh but are absorbed by bones. Soft X-rays are produced by electrons moving at relatively lower velocities than those that produce hard X-rays. They have less energy, longer wavelength, and hence less penetration power compared to hard X-rays. They are used to show malignant growth in tissues since they only penetrate soft flesh but are absorbed by such growths. quantity of X-rays. Quantity refers to the total number of X-rays in a beam. This is sometimes called the beam intensity and depends on the heating current. The greater the heating current, the greater the number of electrons produced, and hence the more the X-rays. Quality refers to the average energy of the X-rays. Sometimes we call it the strength of the X-rays and depends on the speed of the electrons. This in turn depends on the accelerating potential difference between the cathode and the anode. Let's talk about the uses of X-rays, and we start with X-ray imaging. X-rays have very short wavelengths and, unlike visible light, are able to pass through most tissues in the human body. Since bones contain calcium, which is denser than other tissues, they are able to stop some of the X-rays and can thus form a shadow. Just like a hand placed in the path of light casts a shadow behind it, X-rays directed at the body produce a shadow on the opposite side that can be registered on films or on digital sensors. So the bones are clearly visible, while soft tissues like muscles are shadowy. As a result, the two-dimensional images formed by X-rays are useful in revealing fractures within the body. Computed tomography or CT scan is an X-ray procedure that creates cross-sectional images with the help of computer processing. CT images are more detailed than conventional X-ray images and reveal bones as well as soft tissues and organs. A conventional X-ray uses a fixed tube that sends X-rays in only one direction, while a CT scanner uses a mobile X-ray source that shoots narrow beams of X-rays as it rotates around the patient. There are special digital X-ray detectors located directly opposite the X-ray source. As the X-rays pass through the patient, they are picked up by the detectors and transmitted to a computer. Image slices can either be displayed individually in two-dimensional form or stacked together to generate a three-dimensional image that can reveal abdominal structure or help the doctor to plan and monitor treatment. X-rays are also used to detect flaws in metal castings and welding. They are also used in crystallography to study the structure of substances. Since the wavelength of an X-ray is similar to the distance between atoms in a crystal, diffraction can be used to measure the distance between atoms. X-rays are used to inspect luggage for any weapon or unwanted items hidden in them. The X-ray image of the suitcase looks like this. Various objects can be identified: an alarm clock, eyeglasses, a hair dryer, a hanger, shoes, and other items. Here, the object images are displayed in colors according to their specific material. This is made possible by distinguishing between high energy and low energy radiation. And finally, dangers of X-rays. Now, excessive or prolonged exposure to X-rays causes damage to the cell DNA, causing mutations and sometimes death of the cells. Since the effect of exposure is cumulative, it is important that the exposure be limited to as short periods as necessary and as few times as possible.